Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Epen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@epen.info. My guest today is Professor Igor Shovkovy, who is professor in the College of Integrative Sciences and Arts at Arizona State University. His expertise includes theoretical physics, nuclear physics, high-energy physics, and condensed matter physics. Welcome, Igor.
Hello. Very nice to be here with you.
Yeah, thanks for doing this. So our discussion today, we have you're doing some very interesting research. This is very new in many respects. Some in material sciences area, but I want to start with your 2018 paper entitled The Overdamped Chiral Magnetic Wave. You say about 8 years ago, it was predicted theoretically that a charged chiral plasma could support the propagation of the so-called chiral magnetic waves, which are driven by the anomalous chiral magnetic and chiral separation effects. This prompted intensive experimental efforts in search of signatures of such waves in relativistic heavy ion collisions, you say. So what exactly is, I guess, two questions, chiral plasma, and then what exactly are the chiral magnetic waves? And to the extent that, I know that it's very, very new, to the extent that you find some applications for it, what may they be?
Okay, yes, this is a fascinating topic. Actually, I was interested in chiral plasmas for quite some time, and I could very easily explain what that is.
Yes.
In fact, it starts sort of at the concepts of quantum mechanics. Quantum mechanics is, of course, a very interesting field, which is not that new, 100 years old basically now.
Yeah.
But there are some interesting and quite amazing properties in quantum mechanics that we don't really have much experience in everyday life with. One of those things is the so-called anomaly. So the easiest ways to explain that would be to say that there are certain properties that we know in classical physics hold true, but in quantum mechanics, they actually break down. So you expect that something, and I will be very figurative here because the concept of anomaly is pretty deep, and perhaps I wouldn't be able to explain it in 2 words very quickly. But the analogy could probably give you an idea.
Yeah.
So let's say if you take a classical object, a certain shape, square, then it has a symmetry. You could turn it by 90 degrees, it becomes itself. So you cannot distinguish the rotated object from the original.
Right.
And in classical mechanics, there are also some symmetries. We call them symmetries, but sometimes you hear them as the conservation laws. And you could think of them mathematically in a way as changing something in the theory, and the theory will not modify, remain itself. And that in turn means that there are some conservation of charges and some other things that are we calling symmetric in physics. So in classical physics, we have the conservation of the electrical charge. That's one of the analogs of that symmetry that I mentioned. And of course, it's also conserved in quantum mechanics. So the electrical charge is always conserved. You cannot really find any experimental evidence that would tell you something else. But then at some point in development of particle physics, there was also found that there might be some other charge, so-called chiral charge, that could be either exactly conserved or nearly exactly conserved. And that was entertained for maybe like 20 years before people realized that if that symmetry were true in quantum mechanics, there would be very strong contradictions to the experiment. The experiment that I have in mind, it was the neutral pion decay. So there is a particle in particle physics called pion. You could measure how long it lives in detectors, in all kinds of collision experiments, and you will find that it doesn't it lives a little longer than this theory would predict.
Yeah.
And it happens that I said it wrong, by the way. It lives much shorter than predicted by the theory, where this charge would be conserved. So roughly speaking, if there were a conservation of this charge, the decay will be nearly forbidden. In experiment, we saw that it decays pretty well into 2 photons.
Right.
And that was a puzzle for nearly 20 years until it was realized by a couple of genius people in physics that it's actually Adler, Bell, and Jikiv, who realized that there is so-called quantum anomaly, that charge cannot possibly be conserved in quantum mechanics. It's actually broken by the so-called anomaly. So there is a formal procedure of quantizing a theory, and when you are trying to do that quantization for some types of theories, you will find that some of the charges absolutely cannot be preserved in quantum theory, and chiral charge is one of those. So plasma with chiral charge will be called a chiral plasma.
Okay.
Sorry, you were trying to say something.
Yeah. So I was just wondering. So when I hear chirality, I think about we have the same sort of concepts in chemistry and life sciences, right? So there's a directional preference, or when you rotate a molecule 180 degrees or something, it doesn't quite superimpose. Chirality here is not in that way. It's something completely different.
It is not in exactly the same way, but the connection exists. Actually, the connection is the relative orientation between the momentum of the particle, or if you wish, the direction of its motion, and the spin that it carries. And the spin is essentially a quantum concept. Spin truly exists only in quantum theory. So in this context, it implies that actually when we are talking about those chiralities, we mean the relative orientation of the spin and the direction of the motion of the particle. If the particle is moving in a certain direction and the spin is pointing in the same direction, that's called the right-handed particle. If the spin is pointing in the other direction, it's the left-handed particle. And the parity transformation could be also defined in particle physics, and it will be related one particle to the other by this parity transformation, like a mirror image that you mentioned in chemistry.
And so we find in this case, we find the symmetry is broken, right? So what we expect the symmetry were not, if I understand this correctly, Igor, I don't really know much about it. If we expect the symmetry is not broken, we have some expectations, but experiments show us something different.
Right. But first of all, you have to appreciate what means the symmetry in this context. It's not just a symmetry like mirroring right-handed particles to right-handed particles with the direction of motion of spin in one direction or the other. It's actually about the overall number conservation of the particles that are left-handed versus the number conservation of the right-handed particles, left-handed particles, where the spin and the momentum in the opposite direction. So let's say if you created 10 right-handed particles and only 2 left-handed particles, if this were a properly conserved charge, you would never change the overall number of the left-handed and the right-handed particles. But it happens to be violated, which means that some of those right-handed particles could turn into left-handed particles without any penalty.
Right, right. And so that's what we find experimentally?
Well, experimentally, we are not exactly counting the left-handed and right-handed particles because that would be kind of difficult in this kind of situations. But there are indirect consequences of that conservation. In the case of pion experiment that I mentioned regarding its lifetime, you are not really considering even any right-handed or left-handed particles. That is actually the fundamental symmetry of the theory itself. But then when you start calculating the pion decay, you will see that in the absence of this chirality flips, it would live long because the pion would not have an easy natural way of decaying into two photons. But if there is no symmetry, then this flipping of the chirality kind of relaxes the possibilities that exist for it to evolve. And as a result, it can decay relatively easily.
And so that process creates magnetic waves. So what's the connection to the chiral magnetic waves?
No, actually, the connection is still a bit distant.
Yeah.
The thing is that those kind of implications of the chiral anomaly, they existed only in particle physics and in these relatively difficult and quite exotic experiments that you have to do something very special to arrange the system, create those pions, measure their lifetimes, though that was at the level of each elementary particle or so. Now, what was realized starting from about 1980s, although in truth, it was realized fully since about 12, maybe 15 years ago, that there might be some implications of this chiral anomaly even in macroscopic matter, in matter made of special type of chiral plasma. So the chiral plasma is essentially the plasma where the particles are massless, just like imagine electrons would lose their mass and then they would be massless particles. And in such massless system, there will be almost conserved chirality. It's not conserved exactly because of those anomaly processes, but those processes, they're not super often happening. And in fact, they could be very carefully described and carefully accounted for. But with the exception of these chiral anomalous processes, there will be almost conservation of chirality in such a plasma.
And so plasma here is, what is the plasma made of?
Right. That's an excellent question, actually. Well, it depends on the system you are studying. There are many different types of chiral plasmas or approximately chiral plasmas. Even if you take just electromagnetic plasma made of electrons and positrons. So essentially, when you heat up electromagnetic system made of electrons primarily, then at extremely high temperatures that could potentially exist, for example, in extreme environments near compact stars, near black holes, or if you create plasmas made of quarks that could be sitting at the very core of super dense compact stars. Those will be the conditions under which you approximately reach the regime of the chiral plasma. And that's where you might start looking for those conditions, for those consequences. One other system would be the quark-gluon plasma produced in heavy ion collisions, such as at CERN and Brookhaven, where they collide heavy ions at extremely high energies. And when this violent collision happens, you create super energetic region in space with quark-gluon plasma that exists for a brief period of time, but carries some information into the detector, and we could analyze those signals.
Okay. And you said it's massless.
Approximately massless. So approximately massless. The thing is that neither quarks, nor electrons, nor most of the things that people are studying and calling them chiral plasmas are truly massless. So you might say that I'm contradicting myself saying that there is that chirality, even though they are massive. And when they're massive, the chirality can flip from one type to the other. Well, the reason people are calling them approximate chiral plasmas that they have extremely high temperatures. So using this famous Einstein relation, E equals mc squared, if the mass is small in terms of the relative to the corresponding temperature, so in energy units, if you express the temperature as certain mass times c squared, so if that temperature will be much larger than the corresponding Einstein energy equal mc squared, then you will see that this plasma becomes approximately chiral because all of these chirality flip processes will be strongly suppressed by inverse temperature. And that's when you could start thinking about possible implications of chiral plasma.
Yeah. And so, so the chiral magnetic waves that you talk about in the paper, so let's talk a little bit about that. You say that the propagation of those magnetic waves, the chiral plasma could support that.
Right. Well, in fact, we were kind of in this last paper that you mentioned, we are claiming with my collaborators that in fact the plasma is actually not propagating. So when I say it's overdamped, it means that essentially as soon as I'm trying to create it, it doesn't want to propagate. It's like creating a wave in a honey. It damps very quickly and it doesn't propagate. Now, that is actually a relatively recent finding in view of revision of some subtle detail how it happens. But for maybe like 12 years, it was expected that there should exist very well pronounced chiral magnetic waves. And those chiral magnetic waves are kind of very simple. So imagine any wave that you could typically find. I don't know, a sound wave as an example. You create a slight compression of the air. That compression tends to go away locally, it expands, and as a result, it creates a compression in the nearby region of space. So then the next region of space is trying to decompress, and by decompressing, as it happens, it compresses the next pocket of the air. And that's essentially how the wave is propagating. You have sort of forces acting in such a way that something is increasing and then decreasing, in this case, pressure, and it self-propagates. So you could also consider some density waves when the same happens to the density. The density is decompressing in one region, as a result, compressing next region, and so on. So the chiral magnetic wave was supposed to be the wave where you have this alternating densities of regular charge, for example, electric charge, and the chiral charge. And essentially that goes like this. The charge is compressed in a small region of space, then it's creating certain currents, or if you wish, the expansion, but the expansion in a form of some currents that are compressing the next layer also in the way of creating extra chiral charge there. And this extra chiral charge in the next layer then is propagating and expanding and creating, again, a charge compression in the next layer and so on. So there will be kind of alternating in and out waves of electric charge and chiral charge, and that would propagate. Right. And this would be quite unusual because the usual charge density waves in charged plasmas, they actually are strongly damped because of the electrical field. And this would not be damped, presumably, according to these theories that existed for about 12 or 15 years. And we would see some signatures of those in a detector from heavy ion collisions.
Yeah. Since this happens in very, very high temperatures and it's relatively short, do you see any practical applications of this idea?
Right. Well, conceptually, of course, this was first a fundamental question whether they can even exist, and
Yeah.
potentially they do not, in fact, exist because of the underlying physics that happens there, and that was sorted out only relatively recently.
Hmm.
But some implications of these chiral plasmas actually could be measured in the systems, even very simple systems that are not as exotic as heavy ion collisions, extremely high temperatures, and those temperatures are record temperatures anywhere in space, really. They are so high.
Yeah.
The only closest possible temperatures existed only in the early universe. So it is extremely exotic, and you might be fair to say, well, this is unrealistic to have any applications. It's not true for the following reason. If this is a general phenomenon, then actually we could find analogs of chiral plasma in solid state materials.
Mm.
About 5 years ago, maybe already a few years more than that, there was a discovery in physics, the discovery of new types of materials, so-called Dirac and Weyl materials.
Yeah.
What's so special about them is that electron quasi-particles in these systems, they do behave like massless fermions, like massless particles with a spin, and not approximately, by the way, exactly massless particles in this system. And they did appear to be perfect examples of chiral plasmas. So we have some semimetals. They are called semimetals because they are not having a lot of freely available electrons to conduct the current,
Yeah.
but they do have quite a few of them to actually be conducting. So they are semi-metals for that reason. But anyway, it's the nature of the particles that appear there. And by the way, I should probably mention what means quasi-particle. When the electron is moving through vacuum, we know it's just a regular particle with some mass, has some properties, spin, and many other things, charge. When it is behaving as a collective, as part of a collective motion of all the other electrons that are shared between the atoms of the crystal lattice of a given material, then actually they collectively behave very differently. They
Yeah.
could change their mass, they could change their velocity. They actually behave so different that they may appear even as massless particles.
Mm.
And that's amazing, I think.
Yeah. So you have a book that published recently, Electronic Properties of Dirac and Weyl Semimetals. You talked a little bit about what they are. So these massless particles, as you say, can conduct electricity, right?
Well, they are essentially like electrons modified by the medium in which they move.
Okay. Okay.
So they definitely carry charge. They actually conduct current. They respond to the electrical magnetic fields that we apply. So we can probe essentially almost any types of properties that they have. And in fact, I should probably mention that one of these chiral effects that have been proposed in heavy ion collisions, in nuclear physics, in high energy applications, it was for the first time almost unambiguously reconfirmed specifically in Dirac semimetals. It
Yeah.
has not been proven so clearly and to such with such a clarity and such convincing power in high energy physics that those particles actually give the chiral effects that make these plasmas interesting. But in solid state physics, there have been several already types of proofs, including measurements of the currents,
Yeah.
so the resistance, how it changes with the magnetic field, and actually it appears to be in a perfect agreement with the chiral anomalous effect.
So I know that this is sort of new. So do we have these semi-metals? Uh, do we have you produced physically these things?
Right, absolutely. They were produced. They were produced and tested experimentally.
Yeah.
The first discovery happened, as I said, about it's already more than 5 years, 6 years ago or so. The materials, in fact, are not so exotic. In fact, interestingly enough, we knew some of them for a long time. We didn't know what they are and why they are such good conductors. So one of the special things, which is basic property, they have extremely high mobility of these electron quasiparticles, which means that they are excellent conductors.
Yeah.
Some of those, in fact, are alloys that has been known since, I don't know, maybe like 60 years ago. Those alloys were known to be excellent conductors, and in fact, it was even puzzling. How would they have such great properties without understanding that this comes from this special type of quasiparticles that they are? And the reason is that, well, we didn't fully understand the theory behind these particles. There were some theoretical studies here and there, but only about in 2012, there were a series of theoretical papers which realized that some of these materials actually not only are expected to be of this type and have electron quasiparticles that are massless, but actually because of their lattice structure of those materials, they would have these properties that is protected topologically by the lattice structure. And that means, and by the way, when something is protected topologically, like property that they are massless, then actually it's a very robust property because all kinds of little modifications, little impurities in crystals, they always exist. So if it's not protected topologically, usually it spoils. But if there is something that is protected at a topological level by the structure of the lattice, for example, it's very, very difficult to break it down. As a result, these properties, they are actually very robust, very solid. And in fact, this is only in some special type of materials, not in all the Dirac semimetals. For example, those old-fashioned alloys, they don't have the topological protection. In a way, this property is accidental there. But in these new materials, Dirac semimetals, actually it is a property that is very robust, and in fact, it can be now used in practice for applications and much more reliably. Go ahead.
No, I was just going to. So you talk about electronic properties. So I guess that's what you were going to talk about, right? So what are the sort of the electronics, aspects of this? Their conductivity, their use in semiconductors, perhaps. Do they have any applications in sort of next generation quantum computing or something like that?
Well, there were actually some suggestions that some of these materials could be potentially used in quantum computing, but as far as I know, that's probably not as promising so far as some other potential proposals for for quantum computing. But it is not impossible. We were actually, in the book, we were primarily concentrating on some very simple properties of these materials, even such a simple thing as resistance and conductivity. Because even those simple properties, they actually change and become, as I already mentioned, they become very good conductors because of this special type of quasiparticles. In fact, when this massless electron quasiparticles, when they are moving through the materials, they have many obstacles, obviously. They have a lattice they encounter, they have other electrons that they encounter, they have actually vibrations of the lattice that they encounter with. And all of those could actually reduce the conductivity. Now, when they are these massless quasiparticles, in fact, their scattering, which basically drives the, decreases the conductivity, it's actually highly suppressed. since they are massless and the spin and momentum, they are very much locked to each other. If it's a right-handed particle, they will be trying to move in a single direction with the spin in the same direction, and their scattering will be difficult. And if it's not scattering, means it's a very good conductor, or a part contributes to a good conductivity.
So will this take us, Igor, in the direction of room temperature superconductivity, or that is different?
There is a potential superconductivity, and it's also very unusual in these materials. But in fact, there is something even more unusual and interesting. There is a proposal from one of my good friends, a researcher from Brookhaven and Stony Brook right now. He and his collaborator, they propose that in fact there is something like chiral transport that could be used instead of superconductivity. So superconductivity typically requires very low temperatures. Achieving those might be difficult and in some cases actually cost prohibitive. Now, if you consider this chiral conductivity, in fact, it might be happening even at the room temperature. In fact, the higher the temperature of this solid state physics plasma, the better they are chiral particles. So in fact, they were proposing that you could use this for a different type of transport, for essentially chiral transport rather than superconducting transport. And it might be as useful in applications as superconductivity, if not more. But this is not directly superconductivity. Go ahead.
Yeah. Are they analogous? So is the conductivity directional here? Are they analogous to graphene or something like that, or not?
Oh, an excellent question. Actually, graphene is perhaps one of the first clear examples where these Dirac massless electron quasiparticles have been discovered.
Yeah.
Graphene, however, is a two-dimensional flat material, so that of course makes a lot of challenges of its practical application. I'm not saying there are no applications. In fact, there are already so many applications, it's amazing. But now it's, if you wish, these Dirac semimetals are three-dimensional analogs of graphene. So take graphene and to the next level, to the 3 dimensions, and this is your Dirac semimetal. So in fact, yes, all kinds of potential applications in 3-dimensional materials is exactly what we are aiming at. So it's extremely high frequency devices. So one of the things that is very useful for is something that devices that work at extremely high frequencies. At extremely high frequencies, many materials suffer from losses because of those quasiparticles which are not massless. When you have these massless quasiparticles, in fact, you could highly increase the efficiency of all kinds of devices that work at extremely, let's say, terahertz frequencies. And that would be quite amazing in terms of applications. And it's only one kind of snippet of possibilities.
Yeah. And so from my own understanding, so the graphene, you say it's two-dimensional, meaning it's a very thin layer. It's a single molecule layer.
It's a one atomic layer. So if you take graphite that you are writing with and take those flakes that are coming off it when we are writing, then basically those flakes actually, they have very, very many layers sliced off the graphite. But when you go down to a single atomic layer, or maybe a few atomic layers for the bilayer and trilayer of graphene, then that's basically what graphene is. And of course, it's nearly invisible. It's so thin. It's one atomic layer.
Right. But here in this Dirac and Weyl semi-metals, there are no such constraints. You can actually have 3D materials, and they're going to behave a lot better than even stacking graphene to.
Yes, exactly. when you're stacking graphene, you're actually, the more of those layers you stack, the closer you get to graphite and more of the properties of the actual graphene in one atomic layer you're losing. So in this case of Dirac semimetals, actually, it's sort of the other way around. You have a perfectly fine massless quasiparticles, electron quasiparticles in a three-dimensional crystal. And in fact, they're not so rare as it turns out. We just didn't know to look into this direction and how to search for them.
Yeah,
I believe there are already dozens, if not hundreds of materials, probably more than dozens, hundreds of materials discovered.
Yeah, that's really exciting because it sort of opens up a completely new area, right? Obviously we are still in the theoretical realm, but as we go forward from a practice perspective, if the material costs are not high, if manufacturability is possible, then there is potentially a lot of applications, I would imagine.
Yes, that's the hope. In fact, this is perhaps the main idea that is driving an explosion of research in this field, because everybody understands the value of three-dimensional materials that have such amazing properties. It was a dream in 2000, I don't know, 4 or 5, just immediately after the discovery of graphene. Everybody was talking, what about three-dimensional graphene? Well, we have it. Just 10 years after graphene, we got it.
Right. And this discovery was in 2015?
Actually, it's 2014. 2014, right. So theoretical prediction, I believe, was published in 2012.
Yeah.
There were, I think, 2 groups of researchers. One of them is based in Beijing. Yeah. Actually, I forgot where was the other one based. There were people who were trained at some US schools, some China, some in China, and actually that was the theoretical prediction. And maybe in 2014, to the best of my recollection, it was the 3 papers appeared almost on the same day in arXiv at the end of September. I remember like today it was probably the last day of September 2014. And all 3 papers appeared on the arXiv.
Right.
And the next day everybody knew about it.
Yeah, very exciting. We'll take a quick break, Igor. When we come back, we talk about your more recent paper on QCD plasma.
Okay. I'll talk to you in a minute.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So Igor, we are back. We have been talking about the Dirac and Weyl semi-metals, recent discoveries from 2014 that have some very, very interesting characteristics. You have another paper recently, just very recently, last year, entitled Ellipticity of Photon Emission from Strongly Magnetized Hot QCD Plasma. QCD is quantum chromodynamics. So this is some sort of quark plasma?
Yes, exactly. As I was saying, in these heavy ion collisions that you have in Brookhaven at CERN, you create this highly energetic, extremely high temperature plasma. And this plasma is made of quark and gluons primarily. And while studying the properties of this plasma is of great fundamental interest because we don't see that kind of matter regularly in everyday life. But this plasma existed in the early universe And in order to understand our origins, our beginnings, it's extremely interesting to understand what kind of properties this plasma has. And in this paper, we were trying to study some aspects of of those properties.
So right from the Big Bang, so this is an epoch even before atoms formed, right? It was in this kind of a form at that point.
Yes, it was much earlier than the atoms formed. It was actually very briefly, I believe about a microsecond after the Big Bang, that essentially the temperature was of extremely high value, which in the energy units will be hundreds of mega electron volt temperature. And this is the temperature that is created in heavy ion collisions in the form of quark-gluon plasma that comes out of a deconfinement of quarks inside of hadrons. So when we collide nuclei, those are composed of protons and neutrons are in turn made of quarks, but those quarks are kind of trapped like inside of bags of neutrons and protons. They cannot escape.
Yeah.
And in quark-gluon plasma, you create the conditions where it's heated up to such high temperature that they become deconfined. They behave like free particles in this plasma.
And so can we create this, so the quarks are inside neutrons and protons, and you have gluons in there. So can we create this type of plasma with the energies of the Large Hadron Collider?
Yes, we can. We create the plasma with this temperature of like hundreds of mega electron volts. Of course, the reason for that is that we accelerate them to extremely high energies and the speed of very close to the speed of light. At such high energies, they of course deposit this into the collision, and that energy, kinetic energy of the motion, is converted into the thermal temperature of this plasma, and that's how we create high temperature.
Okay, and so what's the implication of this ellipticity of the photon emission?
Right. Well, I probably should step briefly backwards and say that in heavy ion collisions, in addition to plasma itself, you actually also generate very strong magnetic fields.
Yeah.
It's very easy to understand. If you think of the ions that are colliding, they are positively charged, let's say gold ions. And those ions carry electric charge. They are moving past each other. When they are passing next to each other, they are creating the magnetic field, like two parallel wires create a magnetic in between the wires. The same way these ions will be carrying currents and creating, for a brief period of time, a very strong magnetic field in between those ions, precisely in the region where the quark-gluon plasma is created.
Yeah.
And why this is interesting? Well, because some of those chiral effects, they are triggered by the magnetic field. Now, one of the difficulties of identifying signatures of any anomalous effects in heavy ion collisions is to tell actually how big the magnetic field was during those collisions and what kind of implications that kind of strong magnetic field could have on the observable data.
Yeah.
Now, the thing is, theoretical predictions about the strength of the magnetic field are not super reliable at this moment. The theoretical uncertainties coming from extremely non-trivial conditions created. So those are not very smooth, nice ions in the first place. So there are a lot of statistical fluctuations in the collisions. There are a lot of many other uncertainties. And identifying exactly the properties of the magnetic field that is created is difficult. On top of that, the magnetic field may survive longer or shorter period of time depending on the conductivity of the plasma. The more conducting it is, the more magnetic flux can be trapped there for a while. Like in the core of the Earth, we have the magnetic field trapped, the currents are trapped, and the magnetic field is kept without decaying too much too quickly. That's because we have conducting core in the Earth. The same thing there. If we have very conducting plasma, the magnetic field may survive longer period of time. If the conductivity is not very large, then actually the magnetic field can decay very quickly and will not be able to trigger those anomalous effects.
Yeah.
So one of the ideas that I had together with a couple of my collaborators is to look into a way of measuring that magnetic field in some other ways.
So
and one of the ways, sorry,
one quick question, Igor. This plasma, it is not necessarily uniform, right? The composition of that plasma could be different in different experiments.
Well, not only in different experiments, even in the same experiments, unfortunately.
Yeah.
So it's inhomogeneous.
Yeah.
Obviously, it's highly inhomogeneous. If you are creating that plasma from a collision of two ions, even if those ions were exactly spherical and nice and beautiful without any irregularities, even in that case, the plasma that you will create will be created in some sort of overlap region, which you could imagine as sort of almond-shaped region from the two spherical objects passing next to each other.
Okay, so
and the overlap region will be already in homogeneous.
And the magnetic fields generated by that, it's a function of the composition of the plasma?
Largely,
yeah.
It's determined by the amount of the charge that the ions carry and how far next to each other they are passing in this region. So this is the so-called impact parameter. So if you imagine the centers of the two ions passing each other, so what's the closest distance that they pass each other by? That will be called the impact parameter. So depending on that impact parameter and the amount of the charge they carry and the energy they carry, because the larger is the energy of the ions in the accelerator, the faster they are moving, the larger is the current. So all of those things determine. So from every event, you have a different magnetic field. So not only it's difficult to tell how big is the magnetic field in general, but actually it's even changing from collision to collision.
So that's a complication for measurement. So you were going to talk about an idea you and your collaborators came up with.
Right. So of course there are some indirect measurements of many of those things that I mentioned. For example, if the two ions are passing each other, there is, you could imagine, a plane in which they are moving. This is called the reaction plane. So even the orientation of that reaction plane, its tilt, if you wish, with respect to the detector is already a question. But that can be figured out by simply counting the particles. Typically, you will find that in some regions, let's say, if you think of that as equatorial plane, you will see more particles or less, and then you would know that that's that plane, or at least it tells you something about the orientation of that plane. The magnetic field will be typically perpendicular to that plane. Well, basically because it's happening in the region between passing nuclei. But still, how can you tell it in a different way with a different measurement what it was the value of the field in the collision? And the idea is somewhat similar to a thermometer that you use, infrared thermometer that you use to measure the temperature of the body, right? Without touching a person, you could aim at a thermometer and measure the temperature. That is basically what you're measuring is the photons that are coming from a body. And they carry a certain spectrum, and the peak of that spectrum will tell you the temperature of the body. So the same way, actually, we also measure the temperature of this quark-gluon plasma in heavy-ion collision by considering the photons, analyzing their spectrum, and seeing what it tells you about the typical energies, and therefore the typical temperature in this plasma. What we decided is to make one step further and see if we can also tell the magnetic field from the same photons that we are measuring. And the way to tell about that would be to look at the ellipticity of the emission. So roughly speaking, there will be let's say, more photons emitted perpendicularly to the magnetic field rather than in the direction of the magnetic field. And since we have a detector sort of surrounding the whole region, we will see that there will be more photons with some characteristic spectra going left and right, and let's say fewer of them going up and down.
And
not only, yeah, go ahead.
What do you mean by ellipticity?
Well, essentially, yes.
Yeah.
Think of it as something radiating in different ways. And if you look at from left and right, it looks brighter, or there is more photons coming that way than if you look at it from up and down. And that will be essentially ellipticity. So it's like a bulb that is shining non-isotropically, more in some directions, less in the other directions. And then if you imagine sort of plotting the intensity as a function of the direction, you will see that it will be giving you a certain profile of that intensity, and that will be elliptical in shape. So strictly speaking, it will be ellipsoidal in shape, which will be either prolate or oblate ellipsoid.
Yeah, it sounds a bit like polarization.
There is something like that, but polarization typically carries the information about the plane of polarization of a given light. This is not telling you about that at all. It's only the intensity, really. Even though there could be also some signals in the polarization of those photons, but even something as simple as the intensity of the emission will tell you already something. For example, if you have this profile that looks like a prolate, so roughly speaking, more radiation coming north and south and less into the equatorial direction, that in this case, you might say, well, maybe this direction of the prolate axis is actually the direction of the magnetic field.
Right.
And that's exactly what we're trying to figure out. But actually, it sort of happens the other way around. The ellipticity is such that the emission tends to be oblate, at least for those photons specifically that are observed in the detector. The detector typically has some limited resolution and only limited acceptance of different types of photons. So extremely soft photons with small energies will be very difficult to detect. Those that are detected happen to be in the region where they seem to show that the emission is oblate.
Right.
And in fact, that is the prediction. What we find, that if the plasma is strongly magnetized in a strong magnetic field, then actually the radiation will be primarily in the direction of the reaction plane, not perpendicularly to the reaction plane, the direction which is also the magnetic field direction.
So this is a method by which you can you can sort of figure out the magnetic field's parameters.
Right. So, of course, not only we have the thermal emission, so basically the emission changes when the temperature of the plasma changes, but also it's shaped by the presence of the magnetic field. Yes. So analyzing the overall intensity, we can tell something about the temperature. Analyzing the ellipticity, we will hopefully be able to tell something about the magnetic field. Now, the only problem, of course, it's not a foolproof approach, however, I should also mention. The thing is that plasma will be radiating ellipsoidally with this kind of profile, even without the magnetic field, unfortunately. Yeah. And that happens because the plasma is actually behaving almost like hydrodynamic fluid that is expanding primarily in the directions in the reaction plane, and therefore this expansion will also drive somewhat similar signal of the ellipticity. But previous theoretical studies showed that just the hydrodynamic evolution cannot explain enough of this ellipticity that is observed in the detector. So we are claiming that it is the magnetic field that is adding up. And precisely how much it's adding up will give you the idea about the strength of the field.
Yeah. So the challenge continues as you power up.
Exactly.
Large hadron.
It's never-ending challenge.
right? Challenge of measurements. So in conclusion, Igor, I just want to go back to the Dirac and Weyl semi-metals. Where do you think that will take us? If you were to pick one or two areas where we could find practical applications in the next 10, 15, 20 years, where do you think they may make an impact?
Well, I wish I could see the future. I don't know for sure. I have absolutely no reservation telling you that there will be many applications. Most of them will be mundane, simple. They will be in terms of efficiency, in terms of new types of technologies that are simply based on better properties, technological properties, something as simple as resistance, conductivity properties, the response of those properties to different effects, external fields, controls.
Less power use in electronics?
Power use actually is one of those potential applications. It's a huge important goal to be reached to find efficient ways of generating power. Harvesting solar power, and some of these materials, they have exceptional properties in terms of at least not losing some of the generated powers. In some other cases, they are actually speculated to be promising materials for actual solar cells. And the controls and catalysts. In fact, one of the things that we didn't even touch about, there are some very unusual properties of these materials on their surface. So they could be actually very efficient catalysts in some chemical processes. So this huge range of possibilities that the new types of materials open is, of course, incomprehensible at the present. Just like the semiconductors that first were discovered, actually people thought they were useless. In fact, some famous physicists who were the founders of quantum mechanics, they were saying, I believe it was Pauli, who was saying there is absolutely no use for these dirty materials, semiconductors. Who would ever want to use them? Now we know it's far from true. With the discovery of any new type of materials that we didn't have before, the ingenuity of people will just trigger, and we will start making applications because we didn't have this building block before.
Right. Excellent. Yeah, it's really exciting research. Thanks so much for spending time with me, Igor.
Oh, it's my pleasure. I'm so glad we talked about this.
Thank you.
Thank you.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.